All right, thank you. We're going to move on to Maggie, and she's going to chat to us a little bit about rare antelope. So we're getting smaller. We started with Tim, and we're going slightly smaller, you know.
All right. Well, good morning, everyone. I've been warned we might have some load shedding during this presentation, so hopefully I don't get so lucky. Today I'm going to be talking about some declines in rare antelope populations in the Kruger Park. It's a little bit of a shifted title from what you have on your programs because I think it can be partially explained by climate drivers. All right, so for those of you who aren't familiar with the park or the antelope within it, in the mostly the northern part of the park, we have four locally rare species of antelope, the sable, tsabi, roan, and eland populations. And in the late 80s and early 90s, these populations crashed. And so this is a problem for park managers because you want to have a park that has a heterogeneous ungulate population. So one quick sidebar is there's been a lot of work on the effects of artificial water holes on these rare antelope populations and how these water holes may have brought in more predators that are following the more common species that are moving into areas of the park that previously were inaccessible to them because they're further from water sources. And this is a great figure that I love, showing the incidence of waterhole placement in the park that increases. And then after this crash in the late 80s, park management adapted and started closing some of these waterholes as well. And there's a great paper by Norman Owen-Smith and Lisa LaRue, who are in here, that the provision of numerous artificial water points are really affecting this roan crash in this example, and that maybe these populations are recovering. But you'll note that this paper is from 1998, and if we look at this map again, you can see that these populations haven't really recovered as much as we would hope. So the focus of my talk today is thinking about maybe there's some climate drivers going on. So thanks to Reese earlier today, you heard a lot about climate change and how it's affecting ungulate populations. So I'll probably follow from that. And then the second aim of this talk is actually inspired by a conversation with Sam. Like 2 years ago, he asked, why would you treat these four species as a group? Because they have very different life histories and different browsing and grazing strategies, so maybe we can't treat them as a group. Maybe they just coincidentally responded in a similar way. So for the first question, I'm going to focus on a conglomeration of data sets from 1989 to 2011 of ungulate surveys in the park. So a quick sidebar on these surveys is one of the difficulties with working with park data is that there's several surveys that were going on concurrently of the park and then switched over to different methods later on. So first we have an aerial survey of 16 different species in the park, and then there's kind of a concurrent helicopter survey of just the mega herbivores and some of the rare game. And then later on, there was a shift from this very intensive early system of censusing to a much more streamlined transect-based survey. And so what me and my co-authors have done is to kind of translate these surveys, and here I'm using African buffalo as an example because I think it's a pretty good example of all the issues with the data, is to take a measure of effort, how much survey area and time was used to cover these surveys, and get a better sense of the trends in these data. So now we have these animal population counts. We have to think about how they're arranged spatially on the landscape. So I don't expect you to be able to read all of these, but what you can see here is that there's a lot of different landscape types in the Kruger Park. There's 35 that were outlined by Gertenbach in 1973. And so what I wanted to do is to use these landscape types to get a sense of where are these animals on the landscape that are very, not homogeneous, but like the similar landscape cover type. But then to add something about water access as well. So we used distance to river. Here we use 5 kilometers as kind of an average distance to river to break up these shapes so that especially those long ones along the mountains to the southeast, break them up vertically. So we ended up with 166 regions in the Kruger Park. So those are the regions when I talk about regional statistics, that's what I mean there. Okay, so now onto the model. I'm not going to focus too much on the mechanics. You can talk to me later, but just know that I'm using a generalized joint attribute model. Generalized in the sense that it can accommodate very many different data types. In this case, they're all abundance count data, but it could be presence absence. And then joint attribute means we model all species abundances simultaneously. So in future work, this will be really important when we talk about species interactions, but in this case, it's a static model, so there's no interactions being declared here. And then, on the right there, I have, if you want to read more about the model, but I'm not going to say it. All right, so I have here 6 different covariates that I'm looking at: minimum park temperature, rainfall, land cover, whether the river is within 5 kilometers, whether there was a recent fire in that region, and the number of boreholes per hectare to kind of get at that question of the boreholes. To note here is that park temperature is a park-wide scale, and that all the other covariates are measured at the regional scale, and that some of them are changing by year, like climate and management changes, and then some of them are static, so the land cover and the river distance. Finally, as I mentioned, it's a static model, and also I ran it jointly for 16 species, but for the sake of clarity in this talk, I'm only going to be talking about the rare antelope. All right, so to get back to the first question, are rare antelope population patterns largely driven by changes in climate? I've broken up these covariates into 2, one being climate-driven and one being not so climate-driven, although you could argue that fire can really go in either of these categories, but for now I'm putting that in the management category, and we can talk later about that if you want. So to start with the second one, for non-climate-driven parameters, what do I mean by climate-driven responses? Well, so in this case, the dark red is fire that has occurred in the last year, and the light red is no fire. And so a positive response might look something like this, where you have the species is having a larger abundance in those areas with more fires. A neutral response might look something like this, where you have no correlation between fire and species abundance. And then a negative correlation might look something like this. We can also take this, here's the promised load shedding. It seems my microphone's still working. Okay. So we can also look at this in the sense of a graph like this. So on the y-axis, we'll have the species response. It can be positive, neutral, or negative. And I was going to show you these graphs for each of my covariates, and then I thought that's a little bit confusing and too many graphs to show you, so I'm only going to do it for a couple. The first one being fire, because I think it's important to note that while we have all 4 of these rare antelope species that we're looking at have positive responses to fire, everyone else does too, which is something that we expect, right? You know, you have a fire and it increases the nutritive quality of the grasses or the forbs that are coming in. So ungulates like fire, we know this. But then I thought, maybe I'll show it to you like this. So you have the 4 species that we're looking at, and then the column is going to be the covariate and whether it's a positive or negative response, and they'll be a little bit grayed out if it's not as significant as, so for example, all of these are highly significant. Okay, so, and then responses to rivers. Sable and Sabi, not much response, but Roan seem to avoid rivers, and Eland seem to be attracted to rivers. You can remember that for later when we talk about land cover as well. Boreholes, this was a little bit more interesting because given what I had said before, it seemed like boreholes are really driving these species crashes. But one thing to note is that the timeline that I'm looking at is mostly post-crash. So I'm thinking, you know, perhaps it drove the crash in the beginning, but the suppression of antelope populations afterwards maybe wasn't as driven by borehole densities, or maybe removing some of those boreholes in the park was helpful. Lastly, for those non-climate drivers, I have land cover, and so I took those original 35, kind of broke them into broad categories so that they're a little bit easier to understand and model. You don't want 35 categorical variables in there. So first to note is that the alluvial area, which is mostly near rivers, again, we see eland positively responding to rivers. This is to be expected. For shrubby and sparse felt and Mopani woodlands, we see that all of the rare antelope responding positively, except for sable to the shrubby sparse felt. And then for all the other land cover types, there's a negative response. Although I will also point out, again, that fire, all the other ungulates had positive impacts, and then also for sandy felt in the Pundamiria region, there's just low density of ungulates in general. So those 2 aren't really indicative of the rare antelope. Okay, and then on to climate drivers, which is more of the interesting thing here. So first we have temperature, and so I put a graph up here so you can see the temperature increases. One thing that anyone looking at this would say is, well, isn't temperature then just a proxy for time? And I say, yep, you're probably right, so that's moving forward, something I'm going to think about. But in general, all the rare antelope had negative responses, and again, going back to our box plots, you can see that actually they're quite shifted out as a group, and that most other species are responding positively to increases in temperature. which I thought was quite interesting. And then with rainfall, we see negative responses for all but the sable, which makes sense because one thing I didn't mention is that most of these species only live in the north of the park, except sable is pretty widespread at low densities everywhere. So, conclusion for this first section. For climate, yeah, we see some evidence that there's some climate effects. For non-climate, it's a little bit more of a mixed bag. Land cover type is really, really important to these species, as many of you know. So in conclusion for this first question, rainfall, temperature, and land cover type are the most important. But maybe we need dynamic models to tease out climate as a main driver. Some limitations to mention. Again, I said the correlation between increasing temperature over time. Also, temperature here is a park-wide statistic, so I want to get into more region-specific measures. Static models don't account for year-to-year differences, so in the future I'm going to be running a dynamic time series model. And then also to mention, this is the paper with Norman and Lisa. It was about the Lee effects in sable populations. So this is when some populations are at very low densities, then perhaps they have trouble recovering over time, even though conditions improve. So you can check that out if you want. So answer to question one, likely yes, but we need to model dynamically. And so that's going to be the bulk of my second chapter of my dissertation, so stay tuned. All right, and then for the second question that was inspired by Sam over here, is this a coincidental decline? Let's find out. So we're gonna, the way that you read these results is that this is not gonna be a phylogenetic tree, this is using a correlation distance. So species A and species B here are more closely related than species X and Y are because they have a shorter distance on this x-axis. And they're more closely related to each other, kind of grouped together, than they are to between groups. And so if we look at just the raw data, like where are these species occurring on the landscape, you don't really see, I mean, you see some clustering of the rare antelope together, but it's not as clear of a picture. So this is just, how are they using the space? But if we look at clustering species by their responses to covariates instead of their spatial use, then we see that these species do cluster together. And I thought that was quite interesting to see is even if we change the covariates, I think I dropped temperature at some point because I thought, there's the strong temporal variance there. We still see this clustering of rare antelope. So in response to Sam's question, I think they do respond in similar ways to the environment, and maybe this classification of rare antelope is something more than just species that all declined at the same time. So in conclusion, some takeaways. There's evidence that climate change may be playing a role, but we need to do some dynamic time series modeling, so stay tuned. And that similarities in population patterns are due to more than just co-occurrence on the landscape, and they truly are in some way responding to climate and non-climate drivers as a group. And with that, I will thank all of my co-authors and sponsors, and you can find me email, Twitter. Yeah.